Hello, good morning, everyone. Thanks for coming to this talk about Elixir. And the title of this talk, like the official title of the talk, is What Elixir is About. And it was really interesting to prepare this talk because today is like the third or fourth year I'm speaking about Elixir at this event, Erlang Factory. And when I was preparing this talk, I decided to take a look at the previous presentations, the slides. And you know, there was one common thought in all those talks, right? Like there is the backbone, the skeleton was always the same, but it always changed a little bit, right? The things around this skeleton. And it's really interesting because that's exactly software design, right? Be it you're working your application or a library, a framework, a programming language, you have problems. And then you need to come up with solutions to those problems. You need to think about abstractions. And some of those, you think about a possible solution. Some of those, you figure out after 3 months or 6 months that they were not really good, right? And then you kind of need to throw it away, start again from scratch, and think about the problem over again. But on the other hand, there are also abstractions, right? That you think about them initially, they work really, really well, and in the future, it grows way beyond you thought it was possible, right? It open up a lot of possibilities that you end up exploring more and more in the long term. So that was one of the interesting parts of doing this talk, and it's a little bit what this talk is about also, about those abstractions that became more and more important as Elixir grew as a language, okay? And yeah, and this is one of the main points, okay? So to get started with the talk, right, what Elixir is about, I just have one quick disclaimer, which is it's not about the syntax. It was never about the syntax, not even when we started, and definitely it's not about the syntax today. And this is the only slide we're going to talk about syntax. I'm not going to talk about syntax at all during this presentation. And one of the reasons is that we cannot have an objective discussion about this, right? We cannot say, like, which syntax is better, right? Some people are going to say, oh, if you really want adoption, it needs to look like C. Someone is going to say, well, for a functional programming language, it needs to look like something from the ML family. And then Robert Verdin is going to yell from the end of the room, like, it needs to be Lisp. And it's never going to be objective, right? Everyone brings a lot of opinion, and we cannot have an objective discussion about this. So let's get past this, okay? And let's talk about the Erlang virtual machine. So the way I look at the Erlang virtual machine today is that we have 3 main things, okay? So we have data types, and those are the lists, tuples, numbers, okay, that we use in our code. And we have modules, and the modules where we actually have our code, right? It's where we have the behavior, and those modules, they are working with the data types. And we also have processes, okay? And the processes are the entities that are actually running our code, and everything is interconnected, right? Because the modules, they are working with the data types, and the processes, they are running code that is defined inside those modules. And most of the data types, they belong exclusively to a singular process. Okay, so everything is interconnected. And then at the end, right, when you have all of those things, we need to package them with a very nice tooling, okay, to work, to write code, and be productive and whatnot. So what I realized, looking back in retrospect, is that if you look at if we start with processes, right? Processes, they are like the main star of the show when it comes to Erlang virtual machine, right? They are excellent. They are the main entity that run our code. We have the OTP team puts a lot of effort in ensuring the processes. They are efficient. They are also our abstraction for concurrency, okay? And for distribution, that's where the message passing is happening. So, we have a lot of instrumentation in there. They are definitely the main star of the show. Okay, and I don't think anybody here would disagree with that. Modules, they are also quite well developed, right? Because, for example, modules is all code that we have that we run, be it Erlang or Elixir, it needs to exist inside a module, right? Modules, they are also our abstraction for doing hot code swapping. And we even have things like behaviors that allow modules to specify contracts. Okay, so they are very well developed too. And looking back, right, what I think about this is that the data types, when we look at those three things here, okay, they are the one that they were not well developed as everything else. And Elixir came as a reaction to that. Okay, it's one of the examples what Elixir is trying to solve. So to give some examples of why I think data types are not as well developed as everything else, right? We cannot really have custom data types. Okay, records, they kind of aim to add tagged tuples to Erlang, but there's plenty of discussion that in the mailing list, in talks, and the implementation kind of backfired because they are mostly a compiler hack. The tuple modules call, there's a bunch of discussion about it too. And in my opinion, I know that not everyone agrees with this, maps, they are a huge improvement when we are talking about adding kind of like our own data structures, right? So maps, they're improvement because we can have our own keys and then we can specify which kind of values that we want, but they do not officialize tagging. I cannot say, I have this map and this map has this layout, this structure, and then I can tag it, and I know that all other maps with this tag is going to have the same layout. We don't have this idea yet. And if we look at other proposals, so before maps, they were added to the Erlang virtual machine. If we look at other proposals, like the frames proposal from Richard O'Keefe, he actually talks about tagging and why tagging could be helpful to add this idea. So we don't have it yet. That's one of the issues, right? Another issue that when we are talking about data types is that when we talk about polymorphism, in Erlang, we have just one basic way of doing polymorphism based on the data types, which is the ad hoc polymorphism. And we have papers from '88 from Philip Wadler and Stephen Blott. It's almost as old as Erlang that says why ad hoc polymorphism is, it's quite limited and why we need to think of better solutions. We are going to talk about this later, okay? One of the things that actually I first noticed when I started working with Erlang, again, when it comes to data types, is when we want to think about collections. Erlang does not have this idea of collections, okay? You cannot, so we have a bunch of data structures, right? Like sets, lists, arrays, queues, but we do not have a unified way to look at them, to look at collections, to say those are all collections. And this is very common to think about collections. It's very common in a bunch of functional programming languages. And it became actually fantastic in Java 8. So here's some Java 8 code. Java 8 introduced lambdas. And they already had this idea of collections. But when they introduced lambdas, they also introduced this whole functional vocabulary that we are used to work with, like map, filter, and so on. All those functional names and operations, reduce, and whatnot. And when they introduced that, they mixed that with collections. So here we have like widgets, and then we are filtering the widgets by color, and then we are getting their weight, and then summing it, okay? And in this code here, it doesn't really matter if widgets is a list or if it is a set, okay? If it is an array, it doesn't really matter. You can use those functions, filter, map, sum, and whatnot, with anything that is a collection. Right, with anything that behaves like a collection. And this is really, really important because you need to learn just one set of API, right? Just one set of functions that's going to work with everything. And you don't need to learn a bunch of different APIs specific for every data type. And not only that, okay? And still, even in Java 8, they also added the idea of laziness in collections, which again is very common in other functional programming languages. And the whole idea here is that you can see here that the difference is that we are calling widgets.string. Okay? And in order to understand how this works, I will go back to the previous slide. So what is happening here is that we have widgets.filter. And then what this is doing is getting the widgets. Let's imagine it is a list. It's getting the widgets as a list and then filtering. And then after filtering, it creates a new list. And then you're going to call map to int. That is going to get integers, right, but as a new list. And then you sum everything together. So what is happening here is that we are traversing the list multiple times and generating intermediate lists, okay? Intermediate lists, which may not be very good in terms of performance depending on the size of the list, for example. So what laziness does is that when you say widgets.string, next time you call filter, it does not actually traverse this stream, does not actually traverse the widgets list. It just stores the computation, okay? And when you say map to int, it's going to, again, store this computation. It's not going to evaluate it. And just when you call something like sum that actually needs a result, like a number, or when you call toList, is that it's actually going to get all those computations, fold them into a single thing, and traverse the list only once. Okay? So that's one of the things we gain for laziness. And it's very useful if you have, for example, very large lists, or if you have an entity, a collection that is hard, that is expensive to compute. So you don't want to traverse everything if you don't need to. Okay? And that's one of the things that we don't have either. So, given this introduction, right, I think it's time to talk about Elixir, because Elixir, one of the main things that we have in Elixir came as reaction to that, and we are going to explore that in this talk. So every time I give a talk about Elixir, and I said at the beginning that there is a common things that I say every time, and those common things are the language goals. So every time I'm giving a talk, I like to explore whatever I'm talking about from the perspective of the language goals, and we have 3 goals: extensibility, productivity, and compatibility. And those are the 3 topics we are going to explore for the rest of this talk, and use them to explain what Elixir is about. Okay, so let's get started. So extensibility, and there are many things that make a language extensible, right? And that's true for most of a language features and characteristics, right? So when we say like, oh, Erlang is fault tolerant, it's not only one thing. There are many things that play together that makes it easy for us to write fault tolerant software in Erlang. And extensibility is the same thing, right? There are many things, and I want to explore one in particular for this talk, which is data type polymorphism. So this is not the correct name. You can read the paper I mentioned early, but I'm going to call it data type polymorphism in the hope that it's going to be very clear what it is about. So if we go back to our 3 entities that we were talking about, right? Data types, modules, and processes. We have polymorphism with modules and processes, but we don't have it for data types. And what this means is this. We can write this code in Erlang. Okay? If I have processes, I can say I have a process identifier, and I want to send it a message. And we don't care what is that process identifier. We don't care which code it's running, who started. We don't care anything about it. The only thing we care is that that process knows how to handle that message, giving a contract that was established earlier. Right? So basically, it's polymorphic because you can say, I don't care what is this process, as long as it is a process that handles this particular message. Okay? And it can have any shape, right? We don't care. If it handles that message, giving a contract, we are good to go. We have the same thing for modules, right? So here is Erlang code where I'm saying I want to call a function in a module. And modules in Erlang and Elixir, they are first class because we can pass them as atoms, right? So we can pass them around. So I'm saying, no, I don't care which module you're giving to me as long as it implements this function. Right? So again, it's the same idea of polymorphism. And we rely heavily on that. Every time we use a gen server, every time we use a gen event, it's exactly this, right? The gen server module doesn't care what you are passing, the name of the module you are passing as argument with the callbacks, as long as you implement all the callbacks. Okay? So, we don't care as long as you obey this contract. And when it comes to data types, we don't have that. Right? We don't have a way to say, you can give me any data type you want as argument as long as this data type does X. Right? We don't have this X. And one example of why this is useful, and I like to use a lot, is the JSON example. Right? And everything you need to think that needs to use, for example, serialize any kind of data structure or traverse any kind of data structure, okay, is where this polymorphism becomes really useful. So here's how I would imagine, like, we are an Erlang developer, and then we create this JSON module. And what this JSON module does is that it can encode different data structures to JSON. So what we do here is that, we define a bunch of clauses, right? So when I receive an item, and this item is a list, here's how I'm going to encode it to JSON. If I receive an item, and this item is a binary, here's how I encode it to binary, and so on. And the issue with that is that it doesn't, because all the clauses, they are packed in the single module, it doesn't really compose. So imagine that we have this code, right? We have this JSON library. And then Robert, he's working on Luro, one of his projects, okay? And the Luro project has its own dictionary, has its own internal representation of how it represents Lua objects, and he wants to use the JSON library. Okay? The issue is that the Lua project, because it has its own representation, the JSON project has no idea about this new dictionary thing, right? It doesn't know about it. And because Robert needs to depend on it, right, he has like a couple options. So one of the options would be to fork the JSON project, okay, and let it know about his new data type. Maybe if the person who designed the JSON library allow a function to be given a callback, he can try to use this function callback, okay, and then he can kind of use this JSON library. But now imagine that someone come later, Joe, right, he's working on his Erlang project, and he wants to interface with the Lua project, right, and also use the JSON library. So he wants to use both. And Joe also has his own data types, okay, because it's a new Erlang version, right? It's Erlang, so he has a new data types. And what he's going to do now, because the JSON project doesn't know about his data types, okay, so he can say, okay, I want to fork the JSON project to let it know about my data types. But Robert already forked the project, so he needs to now create a fork that has both Robert changes or his changes, right? If he was using function callbacks, he needs to get all the function callbacks and implementation from Robert's project, bring it to his project, okay? And then maybe it will work, right? So it really doesn't compose, right? You cannot like have different projects just extending the JSON library. And the issue about this is exactly because it's just ad hoc polymorphism. All the code is in a single module, is in a single place, while the truth about this is that the data type is the one that knows how to convert itself to JSON. It's not the JSON module, right? The JSON module cannot know about everything, right? The one that knows about that is the own data type, and the data type is the entity we need to ask about, you know, how can you represent yourself in JSON? And this is exactly what protocols in Elixir aim to solve. Okay, is to bring this polymorphism. Okay, so what we can do is that in Elixir we would say, I want to define the JSON protocol, and this JSON protocol has a encode function. And we can call this encode function as any function in our code, like JSON.encode, passing the item. And the thing is that after you define the protocol, you can implement it to any data type that you want. So the person that implements the JSON library could implement the protocols for all the native language types. So he would go and say, the implementation of the JSON protocol for lists is going to be this. The implementation of the JSON protocol for bit strings is going to be this other thing. Okay, and that's it. And then if someone else in the future has their own data type, right, like Robert or Joe, they're just going to say, the implementation of JSON for my own data type is going to be this other thing. And at the end of the day, what we can do is that we can write a JSON library that is extensible to any data type, be this data type existing in the past or a data type that someone defined in the future. So we have basically answered this question, right? Now if I want to say, you know, now that I have protocols, I can say, you can give me any data type that implements a protocol, and your code is going to work. It's a contract that is happening at the data type level. And with this, we can do a bunch of interesting things. One of those things is exactly to introduce the idea of collections into Elixir. So one of the protocols we have is the numeral protocol. And the numeral protocol tells how we can traverse data structures, how we can traverse collections. So here's how I can use the numeral protocol to map over the numbers in the list, multiplying every element in the list by 2. Okay, so it's just mapping over this list. But the same function can be used to map over a range. Okay, and you can, if you define a new collection, if you define a new abstraction, if you define a special queue, a special array implementation, you can teach the null module that comes with Elixir to work with your data types, right? You don't need to re-implement all those APIs. So what is the enumerable protocol, right? Internally, it's based on something called Haskell iteratives. And what this means, the fact that it's based on Haskell iteratives, is that it not only works with in-memory collections, like lists, ranges, and so on, but it also works with resources. It can also abstract resources like file, I/O, sockets as collections. Okay? So here's an example. In Elixir, if you have a path to a file, you can get this file as a stream, as a collection. And then, for example, by default, file stream is going to get a file and traverse it per line. So considering that every line in the file is an entry in this collection. So here's Elixir code to taking the first 5 lines of a file. That's all you need to do, right? You create a file stream, and then you say, I want to take the first 5 entries. By default, it considers every line an entry, and then you take the first 5 entries. It's the same function we use to take the first 5 elements of a list. And the thing about file stream is that it already starts giving us this idea of laziness, because when you say file.stream, it doesn't open the file. It just contains a representation of how we need to open the file when there is a need, get the entities out of the file, and then close it. Okay? So file.stream just returns this representation, and just when we need to actually traverse the file, that the file is open, we get the 5 lines and close it, and we don't even need to traverse the whole file. Okay? So this is a really nice example. We are going to come back to laziness later. Okay? Another example of a protocol is the inspect protocol that we have in Elixir. And this is some Erlang code. So Erlang has a dictionary data structure. And when you create a new dictionary, if you are in the terminal, it's going to spew all the dictionary internals in the terminal. Okay? And you're not supposed to know about this, right? If you're going to check the type specs for the dict mod, it says this thing is opaque, right? You're not supposed to know about this. You're not supposed to fiddle with this. And there are ways that you can do so it doesn't show all that. Okay? But that's what we get. And again, it's the same issue, right? We actually want to ask the data type, what is the best way for you to represent yourself to a developer? And that's exactly what we did with Elixir. So in Elixir, we have a hash dict, which is the equivalent of a dict in Erlang. And the hash dict implements the inspect protocol. So when you are in the terminal and you create a new hash dict, that's what you see, right? And this is really good because if you have an error in your Origin server or if you're logging something, you're not worried about all those dictionary internals, right? You're worried just about this representation. And if for some reason you are kind of debugging some code and kind of want to see what is inside, there is a flag you can set, and then you can see the whole internal representation. But by default, that's not what you want, right? That's not what you care. So you're going to see just this, just the part the bits that matter. Cool. So that was about extensibility. And the basic example I gave here was about introducing polymorphism and allow us to define contracts that say you can give me any data type that you want, and the code's going to work as long as you obey this protocol. Okay? The second one is productivity, and it's going to be really, really short. I'm not going to expand a lot of it on this talk. And one of the ways that we ensure, it's kind of hard to measure, right, productivity. How can we say that one language is more productive than the other? But one way that we ensure that Elixir is going to be productive is by providing very good tooling. Okay? So we have a build tool called Mix. So as soon as you install Elixir, you have this Mix tool that can create projects, compile, and test them for you. We have a package manager called Hex. Eric's going to give a talk about Hex later, which is worth checking out. And Hex is a package manager, and it's really nice because since the beginning, we kind of wanted Hex to be a package manager for the whole Erlang ecosystem. And now we are talking with the Rebar3 folks. I think they're going to mention it on their talk too, integration with Hex, right? And also documentation. You're not going to be productive if we are in an environment where developers, they don't write documentation, right? What you need to do to know how a project works is that you kind of need to go look at the source code. That doesn't work out, right? Documentation needs to be easy to write and easy to read. So just to have an example, okay? If you install Elixir, you can run those 5 commands. And the first one is going to create a new project. Then you go into that new project. And Mix test is going to run the test, going to compile your project and run the test for you. And then Mix hex.publish is going to build a package and release this new project as a package. And then you can run Mix hex docs that is going to generate the documentation for your project and upload it to a version page. Okay, so if you go to the Elixir projects, all the packages released, the huge majority of them has documentation published online, and this documentation is versioned. Okay, and this is really, really good. This is really, really important if you're talking about productivity. Cool. So that was truly really short. And we can get to the last part of the talk, which is talk about compatibility. So compatibility, how compatibility came to be a goal is that when I was first still playing, not really developing with Elixir. I was kind of playing around how we could do with a language and what we can put in it, what we should leave out. I've messed things so much that I was able to break things like, hot code swapping could not work at all for a reason because I was messing something in the bytecode. And then, eventually I figured out that if we are creating this new language, and one of the reasons for this new language is that it's going to run on the Erlang virtual machine, it doesn't make sense to sacrifice the important features that the virtual machine and the runtime gives to us. And then we say, OK, compatibility is very important, and then we put it as one of the language goals. And for a long period, compatibility meant this weird relationship where we would say we don't touch the Erlang part. So if you wanted to use a Gen server, we say like use the Erlang Gen server. If you want to do this, we say like use the Erlang one. And it took time for us to gain confidence that we could start seeing compatibility not only as this distance, right, but also in a way like we are going to value this Erlang foundation, but we are also going to start discussing, right, and bring people from both Elixir and Erlang communities to the discussion to see how we can improve things and take things forward. Okay, and that's the place we are right now. So this last part of the talk, it is going to have two parts, which is what we have right now with Elixir 1.0 and what we are planning for future Elixir versions. Okay. So in Elixir we have supervisors, we have applications, and they are basically the stock ones that come with OTP. We didn't add anything really. So when you're running a supervisor in Elixir, it's exactly the same code as running the supervisor in Erlang. Okay, we didn't change anything in that area yet, but we did some changes, for example, when it comes to Gen server, and we are planning changes when we want to talk about Gen event. Okay, and I really like the changes we did to Gen server. It was actually one of the topics we had in the keynote last year here at Erlang Factory. And the thing about Gen server, right, is that it is a generic server, as the name says. And the issue about that is that sometimes it's very hard for you to look at the Gen server and figure out what it is actually doing, right? Because you need to go hop through all the callbacks until you get and understand what that Gen server is really supposed to do. And sometimes there is no other way, right? Because the Gen server is keeping state and doing computation in this state. But there are cases when you go to the extreme, right, where we create a Gen server only to be about computation. We create a Gen server for executing a task every 30 seconds, right? To execute some particular code every 30 seconds. And there is really no state in there, right? It's only about computation. And we have also the opposite, right? When a Gen server doesn't really do anything, it doesn't really do any computation. Its only reason is to keep state. Right? That's the only goal of it, to keep state, because that's one of the ways we have to share state between different processes in Elixir. So what we did is that we introduced two new abstractions, which are tasks, which is exactly this extreme, where if you want to do something that's only computation, okay, and we introduced agents, which is only about the state. And the benefit of this is that if I'm reading some application code and I see they're using an agent, I know it's about the state. It can not be anything else. And that makes the code, when you look at it the first time, it makes it much easier to understand because this is only about the state. It cannot be about anything else. And the same thing for tasks. Okay, so let's take a look what we gain with those. So a task for Erlang developers, it's very similar, when we say task start link, it's very similar to proclib spawn link that we have in Erlang. The difference here is that we are really pushing forward to the usage of tasks. So when you are, for example, in our getting started guide, we say, instead of creating a process with spawn link, use task start link, because you're going to get nice logger messages, and we can do a better effort in there. Okay, so we're really putting it out. Okay, and task start pretty much with this, right? Just task start link, and it doesn't do anything more. But with time, they started to encapsulate other common patterns. One of those patterns is the async await pattern. We stole the naming from .NET, from C#. Okay? And so this is Erlang code that I already wrote multiple times and I already seen multiple times, which is basically what we want to do here is that we want to start a process to compute something and then read the computed value later. Okay, so this is what this code is doing. Is it gets the current process, right? It creates a reference, and then it spawns a child process that is going to compute something and then send a message with the computed result later. And then when we care about it, we read the result. And this was so common that we said, OK, there needs to be an easier way to do this. Okay, so we introduce async await. So we just say task.async, the function you want to calculate, and then you can do whatever you want to do concurrently, right, with that computation. And when you care about the result, you call task.await, and that's going to wait for the result for the default timeout that we have of 5 seconds. Okay, so that's one of the patterns that we added once we started to have tasks. Another pattern that came once we start to work more and more with tasks is distributed tasks. Okay, so we ship with a task supervisor, and you can start this task supervisor anywhere you want in your application. So what you can do is that you say task supervisor start link and give it a name. And then from another node, I can say task.supervisor.async and ask that task to be executed in the other node, and then I can read the result later. I can also just spawn simple tasks in other nodes, and so on. The Erlang developers, they are actually going to realize that this functionality is similar to what we have in the RPC module in Erlang. Fred even mentioned it last year. But the difference here is that the RPC module is that it starts one June server, okay, for each of your node, and all the RPC calls go through this single June server. And here we kind of have more of a building kit. You can start as many task supervisors as you want, and you're not serializing everything through this one RPC server. You kind of can create many of those, and each application takes care of their own task supervisors. Okay? So those are very useful patterns that came to be, and that we are using them. Okay? And the other one, so that was tasks, which is about computation. And the other one is they are agents, right? And there isn't really much about agents because they're just about state. So what we do is that you start an agent, and you pass a function that calculates the initial state. And then every time you want to update the agent, okay, we send another function that's going to receive the state and return the new state. And every time you want to read the state, get a portion of it, right? Or it all, you just call agent.get. That's going to get whatever we care about, that particular state. And that's really, really useful, right? And one of the main triggers for creating agents, and we saw that happening multiple times, was that people, they would start to learn Elixir, okay, and they would come to our, to RC channel or to the mailing list, and they would say, I just want to read this file and keep this file content somewhere I can access because I don't want to read and parse this file all the time. Right? So they just wanted a very simple agent that keeps some parsed file contents. Okay? But we didn't have agents at the time. Right? And then we would say, what you need to do is that you need to create this June server. And then you need to implement this callback, this callback, this callback. And then you need to implement the client functions. Right? And that was extremely confusing. Right? People, they would really have trouble grokking the whole June server pattern when they were just starting with it. Okay? And then agents, they basically, they solved this problem. And after we introduced agents, we cleaned up some of Elixir code too. And if you look at the commits, it's much, much clearer, right? The parts where you're just keeping state, agent makes the code much more readable. Okay? Cool. So this is like the present. This is what we have now, right? We have tasks and agents. And everything that I'm going to say from now to the end of the talk are the things we are currently researching and exploring for future versions. So one of the things that we can do is that because agents start teaching developers to think about state as a single entity, we can bring some research, for example, from the alvars, right? So we can have agents which are lattice-based. And basically what this means is that we can have agents that if we have multiple processes trying to change this agent, we are just going to expose an API that guarantee deterministic parallelism. Okay, so basically what we can do is that as you are doing more and more parallel computations, with the agent lattices, they're going to guarantee that you cannot have massive results, right? That you're not going to corrupt the state, and depending on the order the code is executed, you're going to have different results. So that's one of the things we're exploring, right? What if we have a set of agents and operations that they are guaranteed to be deterministic for parallelism? And the LVAR's research talks a lot about that, okay? There's even more interesting research happening, which is when it comes to CRDTs, right? What if we have an agent CRDT which allow us to guarantee that we can replicate the reagent state across nodes? So what we can do with that is that imagine that you have like 2 Erlang nodes, right? And they all have this version of this agent. And you want them to be communicating with each other. So if this node writes to this agent, this change should propagate to this other agent, right? And we want to write it in a way where we guarantee that the changes, they're always going to converge, okay? So it's, because you're already thinking about this state, it's not a huge leap to think about those abstractions. And they're going to be really useful when we are talking more and more about parallelism, which is exactly what is coming next, okay? So this is, it's going to be in Elixir 1.1 or 1.2, not the lattices or the CRDT stuff, but better constructs for doing parallelism. This is what we are putting a lot of effort for upcoming Elixir versions, okay? And in order to talk about parallelism, we're going to talk about 3 things: laziness, pipeline parallelism, and the data parallelism. So we talked about collections at the beginning of this talk, right? We had that Java 8 code, and this is kind of how we would translate it to Elixir. We have a widget, which is a list, and then we want to filter calling the enum functions we talked before, right? So we want to filter only the ones that are red, and then we want to get the weight, okay? And we want to take, for example, the first 5, okay? So those are collections, and those collections, they are eager, right? They have the same issue that we had in the Java code in the sense that when I have the widgets, if widgets is a large list, when I call filter, it's going to traverse the whole list and create another list in memory. When we call map, it's going to, again, traverse the filtered list and create another list in memory, and so on. But Elixir has the idea of laziness, and they are called streams. And all we need to do is to get laziness is to replace the enum module by the stream module. Okay, so the code's the same. We just replace the operations we want to be lazy by stream. And then when you want the actual result, you call a function from enum that's going to evaluate the stream and get the result you care about. So we could call enum to list to get a list, or enum sum to sum those results, okay? And here's lazy, right? So the widgets, when we pass it to a stream filter, it's not going to filter the widgets, it's going to store this computation. And then when we call stream.map, is going to store this computation too. And stream.take is going to store this computation too. And when we call enum to list, everything is executed. And what is really nice about this is that when you say stream.take, it's going to execute just the first items. It's not even going to filter or try to map all the other items. As soon as you get 5 that match your criteria, it stops, right? It's not traversing everything all the time. So that's one of the benefits we get with laziness, right? We can work with large collections, even infinite collections, right? It doesn't matter because we can say, give me the first 5 and don't care about the rest. But when we're talking about laziness, it opens up another big possibility, which is if we have this abstraction of the computation, if we have this representation of the computation, what we could do is that we can say, well, it doesn't really matter if this computation is being executed in this process. It could be executed in this process and this other process at the same time, right? Or you could think of pipeline patterns showing up. And this is exactly what we are discussing, is that we want to introduce pipeline parallelism. So this code is the same as the previous slide, except we added this call here, stream.async. And what this is going to do is that, we have all the lazy computations here, filter, map, and take. And when we call stream.async, what it does is that it says, oh, when you want the results, what I'm going to do is that I'm going to create a process to compute everything that you have so far. So everything, all those 3 operations here, everything up to stream async is going to happen in another process, okay? And we can have pipeline parallelism because if you have a bunch of operations, you can just call stream.async multiple times. And when you call stream.async multiple times, each of those is going to start a different process. And then as soon as the data start to come in, the first process is going to perform the first computations, send it to the other process, right? So the other process is computing the first item, and the previous process started to compute the second one. So have many stages in this pipeline, and they're all receiving data, right, and processing them all at the same time, right? So we have this, we have input, and then we have this process that processes some of it, and as soon as it's done with the first, it sends to the next. This starts computing the second, and this starts computing the first it just received, and the data is just flowing through your system. okay? Because we are building everything on top of those abstractions, right? On top of collections, and then on top of laziness. And then, you know, we were looking at this, right? And we say, okay, what is going to be those red boxes, right? What can we put in there to encapsulate this pattern? And then we were discussing about it, and then we thought, you know, is there a pattern in OTP that is about receiving input, right, and then sending this, then processing it, and then sending it out to different entities? And then we said, well, this fits a Gen event, right? So we are extending Gen event to fit well this pipeline of parallelism. Okay? And it's not only pipeline parallelism, it's also about introducing a bunch of data parallelism functions, right? Because the pipeline parallelism, we are parallelizing the computation, right? Like each step does a different computation. So each process is doing a different computation. But sometimes when you have a lot of data, you want all those processes to do the same computation and spread the data around. Like say, hey, now you compute this thing, now you compute this thing, now you compute this thing. And there are many strategies that we can use, right? We can think about farm. We can think about PMAP that starts, for example, one process for every data, and we don't care. If we need, we start like 10,000 processes. Or we can think about chunked PMAP that starts a process for every 10 entries in the data, okay? And basically, what this allows us to think about is the data parallelism, which is exactly a Gen event pool that is receiving input, delegating it to a child Gen event, and sending it as output, okay? When we put everything together, we can really have those pipelines, right, of data coming through and then going out. Cool. So this is what we are actively working on. And what really makes me excited about this, right, is because we are adding those abstractions and we are thinking about those constructs in terms of the Erlang virtual machine and OTP, okay? So what is interesting is that if we look at other languages, if you have a data problem, you would start writing your application in a way that uses like the in-memory collections and whatnot. And then when you start to have a lot of data, okay, you need to completely rewrite your code, maybe start thinking about something like Spark. Okay, you need to think about going into a completely different direction. But here, we can really grow incrementally, right, because of the VM and OTP. Because what you're going to do is that you write your code, and everything is eager. And then you say, oh, this is not as fast as it could be, so I'm going to introduce the idea of laziness, right? And that improves a little bit. And then you say, OK, laziness is not enough. What I want now is concurrency. So we introduce this idea of parallelism, be it the pipeline parallelism or data parallelism. But if at some point concurrency is not enough, right, because we can have distributed Erlang and we can use that, it should not be hard for us to get that and then start running in a distributed setup. Okay, so that's really exciting. And not only that, right, we are going to use all the guarantees we have from OTP for building fault-tolerant software. It allows us to think very well about the failure semantics, right? What is going to happen if one stage fails, okay? We need to think about this stuff, and this environment forces us to think about this stuff, okay? So we have a lot of interesting challenges, right? Even if you are starting from polymorphism, we can start discussing what is the most efficient way of doing the polymorphic dispatch. What is the most efficient way of, when I have this data type, I need to know how to dispatch to the proper implementation, how we can implement this without any overhead, right? One of the common techniques is inline caches, right? How we can add inline caches or implement inline caches in the Erlang virtual machine. That's just about polymorphism, right? As soon as we go up from collections, laziness, and parallelism, there are a bunch of interesting challenges, which is how to provide back pressure, right? If you have data going through this pipeline, if you have one stage that is slow, how can we provide back pressure and how that's going to manifest itself throughout the whole pipeline, okay? If we're talking about data parallelism, which strategy is relevant? Because processes, they cannot share data. Okay, so many of the patterns we have for data parallelism, they rely on sharing the data, multiple processes working with some shared data. We can't do this now. So which one are relevant for us, okay, for the Erlang virtual machine? Yeah, so that's it for the talk. If you want to learn more about Elixir, go to our website. We have a getting started guide in there. We have a bunch of books already available. There's a learning section on the website which talk about different books if you want to get started. And finally, I want to thank my company, Platform Tech. We have decided since early on to invest in Elixir and to invest in the ecosystem. And I'm really excited that allow us to push forward and think about those very interesting problems. And one of the ways, if you want to know what is happening in the Elixir community, is to subscribe to the Elixir Radio newsletter. You receive a pamphlet in your bags that you can get more information, or you can come ask me. And that's it. This is the talk about Elixir. If you want stickers, I also have stickers, and then come talk anytime you want. And we have time for questions?
Yes, why not question?
OK, so questions. Do we have any questions? Oh, yeah.
So in the streaming interface, you had a series of essentially maps there, right? There were no reduces. So when you've got that take 5,
yeah.
You can imagine one implementation is start the stream, let's start an actor for every element in the stream, go do all of this work, and then only take 5 of them. How does the implementation work?
OK, so the question is,
That would be inefficient.
yeah, exactly. So the question is, if we have this code, right? I'm not even going to introduce Parallelism because it's going to answer a question even without. So imagine that this map operation is super expensive. Okay, for some reason, getting the weight, you need to like go to the screen, do something crazy. Imagine this is super expensive. We just care about the first 5, right? So we don't want to map everything. We want to take just the first 5 that comes out. And this is exactly what is going to happen here. As soon as you get the first item comes, okay, and then if it's filtered, it's going to stop here. But as soon as you pass 5 items, it's not going to compute anything else. It stops there, okay? So, so that's one of the ways. And then we are introducing parallelism. It's going to depend a lot which of those strategies you are using. Because, for example, chunked pmap is going to start them in chunks. And so if your chunk is 100, you're going only to take 5. The 100 is going to be processed at the same time because that's the kind of granularity that you chose. Okay, so that's why we need to think about different strategies too. Because although this is going to cut off as soon as you get 5, maybe you're doing it in eager steps somewhere before. Did I get to answer your question?
Yeah, I guess kind of. So if you've got, let's say you've got 10 things in that map, one way to guarantee that you're only going to do 5 computations is do one all the way through the pipeline, then another all the way through the pipeline. Another, oh, I reached my 5.
Oh, I see, yeah.
And so I'm saying if there's another alternative where you're trying to do even that streaming computation in parallel, but take advantage of the fact that you know that you only want 5, is that possible?
Yeah, so probably again, it's going to depend a lot on your strategy. Because, for example, if you have a farm processing, let's suppose you have a farm or master-slave setup doing 8 at the same time, you're always going to have some going above this 5 limit, right? So it really depends on the strategy. And that's why we need to think about different strategies when it comes to computation, right? Because you say, like, OK, how can I guarantee the 5 cutoff? It's going to really depend on how you are splitting it apart. Okay, and when you put everything together, is one of the concerns you need to have.
Okay, so the
cool.
Yeah,
you need to think, yeah. Yeah.
Because we need to go to the next talk now.
OK, so come talk to me right after the talk if you have more questions. That's it. So thank you very much.